All right, well, we have made it. It is our last lecture of the semester. To give you the heads up, what I'm going to do for this lecture's content, I'm going to break it into 3 videos. Makes it a little bit easier for me to upload as it turns out. And it also, I think, highlights the main topics of today's lecture and at least organizes it for your thought processes. So this will be the first video of the 3, okay? So this is the first of the 3. It's going to be about operating electrochemical cells under non-standard conditions. Now last week we learned all about computing the standard cell potential, E0, right? That was our symbol for it. You probably remember that. And that was when we had 1 molar concentration of ions, 1 atmosphere partial pressures of gases, and of course 298 Kelvin. Those were our standard conditions. But sometimes electrochemical cells deviate from those standard conditions. We need to know how to deal with that, okay? So what happens when cell concentrations are not 1 molar or 1 atmosphere partial pressure of gas? The situation, of course, is going to change. That's a good thing, all right? It may seem like a bad thing because we got to learn a new equation, but it's actually a really good thing because it opens a field called potentiometry, where we can actually measure the concentration of ions based upon the cell potential. And we're going to learn how to do that with an equation here in a second. But if you're not following along, I'm going to draw a picture here down at the bottom, or use these pictures to help explain exactly what we're talking about in no uncertain terms. So if we operate an electrochemical cell under standard conditions, this is the same cell that we were talking about at some length. It's kind of the textbook example, where you oxidize zinc and you reduce copper. In this electrochemical cell, we have 2 beakers. This one over here has got the zinc 2+ ion. This one over here has the copper 2+ ion, okay? Those ions dissolved, and we've got 2 metallic electrodes. This one made out of zinc strip. This one's made out of a copper strip of copper metal. 2 electrodes. We set up this electrochemical cell between this salt bridge, and if the concentrations of zinc 2+ ion in the beaker is 1 molar, and if also the concentration of copper is at 1 molar, and if we are running this reaction at 298 Kelvin, we are working under the standard conditions. And because that, when our voltmeter reads the 1.1 volts, that is our standard cell potential, because we're running this experiment at standard conditions by definition. Now this lecture is going to be all about the non-standard case. What do we mean by that? Well, one thing we could do is change the temperature, but we're not doing that here. Instead, we're changing the concentration of the ions. Instead of running at 1 molar and 1 molar, we're now going to run this experiment when the copper's 2 molar concentration in this beaker, more concentrated, and the zinc is only 0.01 molar over here. The concentrations are no longer 1 molar. This is not standard conditions. It's a non-standard case. So it turns out that if you set this experiment up and you measure the cell voltage, it changes. No longer is it the 1.1 volts. Now it's 1.17 volts. The voltage has changed because the concentrations of our reactants change. Now, again, we're going to have to account for this mathematically. It takes a little bit extra work. We've got to learn a new equation. But because the voltage change, it opens up a new field of science to us called potentiometry. And in potentiometry, we measure the voltage that our voltmeter might read and relate that through an equation we're about to learn about back to analyte concentration, or the concentration of the substances. So we can actually measure the concentrations by measuring a voltage. Let's see how that works in more detail. To help us understand this, we have to become introduced to a new equation. You can see that my topic got cut off here, so I'm going to have to write the name of this out for you. Nernst, the Nernst equation. It's a famous equation in electrochemical circles. And these 2 equations on this slide are indeed forms of the Nernst equation. Really, both of them are. Let me explain the differences. We'll start with the one on the top, okay? Let's look at what this Nernst equation tells us. Well, the first thing that we see is that E cell is equal to something, okay? Now what is E cell equal to? E cell is equal to E0 cell minus RT over NF times the natural log of Q. E0 cell equals RT over NF natural log of Q. Let's break this down. This first term, E0 cell, we've seen that before. That's what we calculated last week. That is our standard cell potential. That's the value that you can calculate using those numbers on the table. That's what our voltmeter would read if we were operating under standard cell conditions. Now, of course, we're not. So where does that come into play? What does our voltmeter read under the non-standard conditions? Well, actually, that's what this number is all about. This first number is what our voltmeter would read, or what the cell potential is under non-standard conditions. Notice there is no zero or naught, but there is over on the right side, isn't there? There, okay? That always tells us, indicates standard conditions. So what does this equation say? Well, to figure out what the voltmeter would read under non-standard conditions, we take what it would read under standard conditions and then we just subtract a number. What do we subtract? Well, we subtract a value that's equal to RT over NF times the natural log of Q. Now there's lots of variables here, but we've seen a lot of these before this semester. First off, the R. That's nothing more than our gas constant with units of joules per mole per Kelvin. Has a value of 8.3145. What about T? Well, T is the usual case. It's the Kelvin temperature. We've seen that a lot this semester. Kelvin temperature times R is our numerator. In our denominator, we multiply N times F. F is that Faraday's constant, the charge on 1 mole of electrons. It's 96,485 coulombs per mole. And N is the number of electrons that are involved in the balanced chemical reaction. The number of electrons are transferred to make the redox reaction go as it is written in the overall balanced chemical reaction. Lastly, there's Q. Now here we take the natural log of Q. That is the reaction quotient. Now, you may have forgotten what Q is, and I want to remind you at this point. Q is nothing more than products divided by reactants. It's just like an equilibrium constant where we raise each product and reactant term to the stoichiometric coefficient. But the difference is these numbers that we put in for our partial pressures or molarities are non-equilibrium concentrations. And that's how we compute the reaction quotient. They're not equilibrium concentrations, they're non-equilibrium concentrations. When we work an example problem in a few minutes, we'll get more into that and you can see exactly what I mean. But this is how we compute, using the Nernst equation, the E cell, what the voltmeter should read under non-standard conditions. Okay, we're going to need to know how to do this. You'll see it in the homework, probably also see it on your final exam in a question, okay? All right, now, because there are so many constants in this term right here, we can start to simplify this equation some by plugging in the values for the constant. So we're going to plug in a number for R. We're going to plug in 298 for our temperature. Say that we're going to do this at room temperature. We're going to plug in the value for F. And we're also going to convert the natural log into the base 10 log. Turns out that the natural log can be related to the base 10 log, an equation that looks like this. There's this constant multiplicative factor of 2.303 involved. So when we do this conversion from natural log to base 10 log, we're also going to have to account for that. But if we do all that, if we plug in the constants, account for this conversion to log, we can write the Nernst equation in this form, which is probably the more familiar form that you all are going to use. Very frequently, we make measurements at 298, and we can use this one, the simplified version. Looks very simple. It says that E cell, the number that the voltmeter would read, is equal to E0 cell minus 0.0592 over N times the log of Q, the reaction quotient. This is our Nernst equation to allow us to compute the cell voltage under non-standard conditions. Now, I want to show a practice problem using this because it is an important concept. So let's try that at this time. Let's practice. To do this, let's determine the cell potential for an electrochemical cell based upon the following two half reactions. We're given one reaction for oxidation, a separate reaction for reduction. We'll have them broken up into half reactions. Now, if we're going to solve for the non-standard cell potential, I guess you can follow this series of steps, okay? The first thing that you really need to do to solve any cell potential, figure out if we're working at standard or non-standard conditions. Now, if I go back and look at this problem here and the reactions for the oxidation and the reduction, how could I tell that this is not standard conditions? Just a couple things I cue in on right away. This one. Are those concentrations 1 mole per liter? They're not, are they? For a standard condition cell, you gotta have 1 molar concentrations of everything, all ions that are present. We don't have that. So we know we are certainly working under non-standard conditions here. That makes a lot of sense since we're trying to highlight use of the Nernst equation. You use the Nernst equation for non-standard conditions. So what's our next step? Well, step 2 is to break the overall reaction into half reactions. Okay? Now that's already kind of done for us here. We have a half reaction for our oxidation. We also have a half reaction for our reduction. I might choose to give you in the problem the overall balanced redox reaction, and you would actually have to break it up into half reactions. But that's something that we did, over a week ago when we were learning to balance these redox reactions. So I think that you can handle that, okay? You just have to identify what's being oxidized and what's being reduced. You have to follow those rules, and then you can break up the half reactions. Here, that's already done for us. Now, because the Nernst equation needs a value for each cell to plug in, we're going to have to find it if we're not given that. So our next step in the process is computing the E0 cell. This is the standard cell potential. So let's talk about that. How are we going to compute E0 cell? How can we compute the standard cell potential for this case? So I move on to the next slide. We're given, again, our oxidation and reduction half reactions. And perhaps you remember from last week, if we're going to compute E0 cell, we have to find E0 for the reduction, or the cathode, and subtract E0 for the anode, or the oxidation. Just subtracting two numbers. Now, to help us do that, we need to figure out what our standard reduction potentials are for both of the half reactions. So we have to look them up in a table. So I'm going to my table of standard reduction potentials, and I see that E0 for the copper half reaction is a positive 0.34 volts versus the hydrogen electrode. And I'm also looking in my table here, and I can see that E0 for this reaction involving the permanganate to go to the MnO2 specifically. If I'm looking at that voltage, it looks like it's right here, positive 1.68 volts, okay? So that's my two reduction potentials for the chemistry of interest. So I need to take my half cell reduction potential for the reduction, 1.68 volts, and subtract the value for the oxidation. Here that's a positive 1.34. If I do the math, it looks like I get 1.34 volts for my E0. That is my standard reduction potential. Now again, that would be what the voltmeter would read if my concentrations of all my ions were 1 mole per liter, but they're not. So I have to fix for that. I have to correct for that, right? So looking back on my steps, I've now done the first 3, and now I can go about the business of correcting for the non-standard case. The next thing I need to do to help me with this is to balance the reaction for mass and for charge. This is a crucial step for us because it's going to allow us to figure out what N is, and remember that variable lowercase n is needed for our Nernst equation. So to help us with that, we need to balance the overall chemical reaction. So what we're going to do is we're going to return to the half reactions under study. The one for the oxidation and the one for the reduction. So for the oxidation, we have copper solid getting converted to copper 2+. And this is a 2-electron process. Now for balancing, we go about it the standard way. we balance every element except for oxygen and hydrogen first. Now, in this first reaction, that's only copper, and copper is balanced. We have one on both sides, no problem. There is no oxygen, there is no hydrogen, so this reaction is mass balanced. And by adding 2 electrons on the right, we also charge balance it, because if I add these 2 negative charges to a 2 positive, that makes a net 0, which is the same charge we have on the left. So this first reaction is both mass balanced and charge balanced from the get-go, and it's all set, okay? Now what about the second reaction? The one involving the permanganate, the MnO4, okay? Let's forget these numbers are here right now. I'll get back to it in a second though. So we take our MnO4, we have 4H plus, 3 electrons, MnO2, 2H2. This was specified in the problem, okay? But otherwise you'd have to kind of balance it. That's going to be a little bit hard to do because it's already spelled out here, okay? But again, you go through the same process. Every element except for oxygen and hydrogen. We start with manganese. Manganese is balanced, 1 on each side. What about oxygen? Oxygen comes next, don't forget. So if I was balancing this, I'd say, oh, I have 4 here on the left. I only have 2 here. I need to add 2 waters. So notice that's what's done. 2 waters are added to balance the oxygen. And then we'd balance the hydrogen. Oh, I've got 4 on the right. I need to add 4 back on the left. And I do that by adding H+. So again, standard protocol for balancing these redox reactions. So it's mass balance at that point. Then we need a charge balance. I've got 0 charge on the right. Before I consider these electrons, I would have 1 negative here and 4 positives here. That makes what? A 3 plus net over here on the left. I have to correct that. And of course I do that by adding these 3 electrons into the mix. This is the standard protocol for balancing these reactions, okay? So at that point, I would be said to be mass balance and charge balance in both my half reactions. But I would have this issue. My oxidation makes 2 electrons. My reduction requires 3. This is a problem. My reduction needs 1 more electron than my oxidation produces based upon these balanced chemical equations. I gotta fix this. Now remember, the way that I fix that is by multiplying each reaction by an integer number required to make the electrons balance. Oftentimes that results from like cross-multiplying, okay? So we take this 2 and multiply the second reaction by it, and we take this 3 and multiply the first reaction by it. Basically, that's kind of what I mean by this cross-multiplying business. And in the process, that yields 3 copies of copper, solid, 3 of these, and 6 E minuses for that top reaction. Now we're also going to multiply that second reaction, the one involving the permanganate, by 2. So we'll have 2 MnO4, and we're going to have 8 H pluses. I'll have 6 electrons. 2 MnO2. This should be MnO2. And then we're going to have 4 H2O. Okay. So now, because I got 6 electrons here, 6 here, they cancel each other out, and I can combine these reactions in confidence. And if I do so, I bring everything else down. So I'll have my 3 copper, my 2 MnO4 from here. I'll have my 8 H pluses that I bring down. On the right side, I'll have my 3 coppers. I'll have my 2 MnO2, and I'll have my 4 waters. Everything else comes down, and this reaction is now balanced for mass and charge. This is our balanced chemical redox reaction. Now again, if this was operating under standard cell conditions, 1.3 volt, 4 volts should be what I see on my voltmeter. But because I'm not operating under standard conditions, I have to take one more mathematical step. And what that step involves is use my Nernst equation to compute what the standard cell voltage, or what the cell voltage would be under non-standard conditions. And that's what I do. So I go to the form of my Nernst equation that we just learned about. E cell is equal to E naught cell minus 0.0592 volts over N times log of Q, the reaction quotient. And I start plugging and chugging, figuring out what my non-standard cell voltage will be. It's as simple as that, okay? That's where we're headed from here. So I take this 1.34 volts that I found in a previous step for my E naught up here, and I plug that in for my E cell. In the numerator, I still have, of this fraction, I still have 0.0592. That's just a Nernst equation factor. But down here in the denominator, I've got n, this lowercase n. Remember, that's the number of electrons that are transferred in the balanced chemical reaction to make it run as it's written. This, finding n, is why we have to go through this process of balancing the reaction and why it's so important, okay? I want to look back at that. How many electrons were transferred and involved in balancing this reaction as it's written? Well, you look here, you say, oh, 2. Or is it 3? Or is it 6? I think n should be 6. And the reason why is because when you write the overall balance process, this one right here, and you combine those reactions in that last step, that is how many electrons were required to make that reaction happen. You needed 6. So we had to multiply that first reaction by 3 and the second one by 2 to make it work, right? So my n is going to be 6 here. And I have to balance my equation to figure that out, okay? Finding that n is sometimes the most difficult part of these problems for students, okay? And I wanted to harp on that just to show you how it's done. But n will be 6 here, okay? Now for this last term, I need a q. Q is my reaction quotient. Now remember, reaction quotients are defined just like equilibrium constants for the overall chemical reaction, except they are for non-equilibrium concentrations. That's the big difference, okay? So if I'm writing a Q expression for this overall balanced chemical reaction, I first key in on my products, of which there's 3. First one's copper 2+. It looks like I'm going to have to raise that one to the 3rd power because of that 3 in the stoichiometry of the reaction, right? Right there. And my other reactants are MnO2 solid and water. Do solids and liquids appear in our equilibrium constant expressions? They don't, do they? So the numerator of this fraction is now complete because the only thing that appears is this aqueous ion. But what about in the denominator? In the denominator, I have to have my reactants, don't I? Well, my first reactant is copper solid. It's a solid, it doesn't appear in the equilibrium constant expression. But look, my next reactant is an aqueous ion. That one needs to appear, doesn't it? So I write a term for the molarity of my permanganate ion, MnO4 minus 1, and I'm going to square that one by virtue of the 2 in the reaction stoichiometry. And likewise, it looks like my next term is also going to be for another aqueous ion, which is H+. So I need to write a term for H+. And it looks like, boy, I need to raise that one to my 8th power. That's a little unusual, but that's what I need to do by virtue of that 8, don't I? But with that said, I've finished writing my my Q expression on my reaction quotient. So I plug that in for Q right here. And you can see that I plug in my molarities in that next step that were stated in the problem. These were given to me. If I look way back to the problem, notice that the concentration of the copper is 0.01. The concentration of the permanganate is 2. The concentration of the H+ is 1. So those numbers are given to me. I simply plug them in, raise them to either the 2nd, 3rd, or 8th power, as the mathematics suggests. So no big surprises, right? So from this point, you just do the math, and you end up with E0 minus a negative 0.065, which leads to 1.41 volts as being the answer to this problem. So basically, if you did set up this electrochemical cell under these non-standard conditions that were specified right here for these reactions with these concentrations, what this problem says is that the cell potential that your voltmeter would read would indeed be 1.41 volts once all is said and done. Alright, so what we've just shown is use of the Nernst equation to compute non-standard cell potentials. And again, the form of the Nernst equation tells us that the numbers that are important are E0 cell, that's our standard cell potential. That basically is determined by what the cell actually is composed of, what chemicals, right, and their native redox properties. And then we correct for non-standard conditions using the second term by subtracting 0.0592 volts divided by n times the log of our reaction quotient. Again, we use this equation at 298 Kelvin. That'll be very common, but it's really only for that temperature. Okay, that's important because to get this factor 0.0592, we had to plug that into this equation. So really this second equation here in the brown box is only for 298 Kelvin. All right, so that's the first part of today's lecture. There'll be 2 more videos on different topics. Let's go ahead and watch those. Take good notes, all right?